Hello, welcome to today's lecture, Math 1C. We're going to start chapter 11. Chapter 11. We're going to talk about sequences and series. Very well. First of all, definition. What is a sequence? A sequence is actually a function. A sequence is a function. What do I mean by that? It means that it has a domain and it has a range. A sequence takes values in the domain and maps them to the range. For sure, the domain of your sequence is either n, natural numbers. Sometimes you can work with whole numbers as well. Whole numbers. So a sequence is a function. It takes values in the domain, either natural numbers or whole numbers, and map them to a range, which is usually R, or real numbers. That's how we define a sequence. So we usually denote a sequence by, we denote a sequence by f of n. So our variable, since it's coming from natural numbers or whole numbers, is denoted by n, or you can denote it by a sub n, a sub n. So we mentioned that the domain is either n, or the domain can be the whole numbers, and the range is real numbers. So usually the range of a sequence can be denoted by curly brackets a sub n. We list all the terms, if it's finite, we list all the terms of the sequence, and we say that, hey, the range of this sequence is actually the definition of this sequence. Again, if it's finite. If it's infinite, you can say that, hey, this is just R, or subset of R. Very well. So for a sequence, we can list the terms of a sequence by plug in natural numbers for n. So here you have a sub 1, comma, a sub 2, comma, a sub 3, comma, a sub 4, and the general term a sub n, and you can continue this process, a sub n plus 1, comma, the rest of it. A sub 1 is called the first term of the sequence. A sub 2 is called the second term. A sub 3, the third term, the fourth term, and a sub n is usually we say that it's the general term. Perfect. So let's go over some examples to see what's going on here. example of sequences. So the following are just some sequences. The first sequence is the sequence n divided by n plus 1. The second sequence is b, defined as negative 1 to the n plus 1, divided by 3 raised to the n. C, you have a sequence, these are all functions. All functions, n minus 3, inside the radical. Then here you have, for example, this sequence here, which says that, hey, I have function cosine pi times n divided by 6, and so on. Take a look at each of these functions. The first sequence can be defined as f of n, which is n over n plus 1. This guy, we can call it gn, which is equal to negative 1 to the n plus 1, divided by 3 to the n. We can call this by h of n, which is square root of n minus 3. And here you have I of n, which can be defined as a trig function cosine pi n divided by 6. Okay, note that since you have functions, you can find the limit, you can talk about taking the derivatives and taking the integrals. So note, since we have functions, we can find the limit, we can graph them, and the rest of the properties that we discussed for functions in algebra, in pre-calculus, in Math 1A and 1B. Another example for you. Suppose you have some terms of a sequence and your goal is to understand the general behavior or the general term or the function related to that sequence. Take a look at this. Example, let some terms of a sequence be given as, okay, here you have 3 over 5, comma, here you have minus 4 over 25, comma, you have 5 over 125, comma, then you have negative 6 minus 6 over 625, and the rest of them. Question says, what is f of n? What is the general formula for this sequence? Okay, perfect. So we know that the first term, a sub 1, is equal to, a sub 1 is equal to 3 over 5. The second term is minus 4 divided by 5 squared. Okay, a sub 3 is 5 divided by 5 to the third. So take a look at this. You see a connection between the index and the exponent. So for now, you can write this way. On the denominator, whatever my index is, that index is equal to the exponent. Index is 1, exponent is 1. Index is 2, exponent is 2. Index is 3, exponent is 3. So on the denominator, you have 5 raised to the n. Very well. If n is equal to 1, you have 3. If n is equal to 2, you have, for a moment, forget about this negative sign. You have 4. If n is equal to 3, your numerator is equal to 5. So what is this? This is 1 plus 2. This is 2 plus 2. This is 3 plus 2, and so on. So you have the index plus 2, n plus 2. Now I expect you to ask, what about these negative signs? If n is equal to 1, the number is positive. When n is equal to 2, you have a negative sign. So it means that I have multiples of the negative sign or negative 1, and since it is positive for odd numbers, I add 1 to it. So it seems like the general formula for this sequence has this format. By analyzing your terms, you can come up with the general format of your sequence. Example, Fibonacci sequence. So Fibonacci sequence is defined this way. Suppose the first term is 1, suppose the second term is 1, then the rest of the terms are going to be the sum of previous terms. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on. So we see that we can define this sequence recursively this way. We say that a sub n is equal to a sub n minus 1 plus a sub n minus 2. So the general term of your sequence is the sum of previous consecutive terms. And n is greater than or equals to 2. A sub 1 is equal to a sub 2. Both of them are equal to 1. Very well. So let us talk about the limit of sequences. That's how we define a convergent or divergent sequence. Let's write down the official definition of convergent or just the limit of the sequence, then we talk about it. Definition of limit of a sequence. So a sequence like a sub n has limit L. L is a constant. L is a number. L is a constant, just a number. And we write the limit of the sequence a sub n while n goes to infinity is equal to L. If the general term of the sequence n goes to infinity is getting closer and closer to L. So if your y values are getting closer and closer to L when n goes to infinity. In mathematical format, you write it this way. You say that the limit of a sub n while n goes to infinity is equal to L if for any positive epsilon there is a natural number like n, a natural number like n, such that if n is greater than that natural number on your domain, absolute value or the distance between an and L is very small. In mathematical format, we define the limit this way. We say that the limit of an while n goes to infinity is L, is a constant, is a number if you take any small number, 1 over 1,000, 1 over 10,000, 1 over 1,000,000, epsilon is a very small value on x-axis. I'm sorry, on y-axis. There is n natural number like n such that if n is greater than n, if n goes to infinity, it means that n is getting bigger and bigger, then the distance between an and L on y-axis is very small. Very well, let's go over some examples to see what's going on with the sequence, the limit of a sequence. So we're going to use the techniques that we learned in Math 1A to take the limit of functions. Math 1A limits. Okay, for example, question says, hey, here you have this sequence. An is defined as n over n plus 1. Find the limit of this sequence. Find the limit of a sum. So, limit of a sub n while n goes to infinity. Think about this function as f of x equals to x over x plus 1. They're equivalent to each other. To take the limit of this function, you have the limit of x divided by x plus 1 while x goes to infinity. Okay. This is the limit of n over n plus 1 while n goes to infinity. Remember that in Math 1A, we learned that since the degree of the numerator is equal to the degree of the denominator and n goes to infinity, this is equal to the leading coefficient of the numerator divided by the leading coefficient of the denominator, 1, and it is equal to 1. Okay, the same concept. Since the degree of the numerator is 1, the degree of the denominator is 1. It means that the limit while n goes to infinity is 1 over 1 or 1. Taking the limit in Math 1a, taking the limit of a sequence in Math 1c. So you say that the limit of this sequence is equal to 1. More examples. There you go. Suppose you have an. So let me write this here for you. An 1 over n, an 1 over n squared, an 1 over n cubed, an 1 over n to negative 1, and an 1 over n to negative 2. Here, I'm giving you different sequences, and the goal is to find the limits. Again, if you remember Math 1a, limit. The limit of 1 over x, while x goes to infinity, is 1 over infinity, which is 0. The limit of 1 over x squared, while x goes to infinity, is 1 over infinity, 0. The limit of 1 over x cubed, while x goes to infinity, 1 over infinity, 0. But the limit of 1 over x to negative 1, since you have a negative exponent, first you have to write this expression with positive exponent. So you get the limit of x while x goes to infinity. And if you are working with limit at infinity, you say that it is infinity, or you say that it doesn't exist. Does not exist. And the same here for limit of 1 over x to negative 2 while x goes to infinity. This is limit of x to 2, x goes to infinity. Again, if you're working with limit at infinity, you say that it is infinity or just doesn't exist. Exact same concept here. The limit of an 1 over n, while n goes to infinity, 1 over infinity, 0. Limit of 1 over n squared, n goes to infinity, 0. Limit of 1 over n cubed, n goes to infinity, 0. Limit of 1 over n to negative 1, which is the limit of n goes to infinity. You say that it doesn't exist or goes to infinity, does not exist. Or finally, the limit of n squared, n goes to infinity, infinity or doesn't exist. The same concept. Another example for you. Question says, find the limit. You have this function, ln of n divided by n. Ln function of n divided by n. Okay, again, in Math 1a, you learn that the limit of ln of x divided by x while x goes to infinity is infinity over infinity. So here you can apply L'Hopital's rule. This limit is equal to the limit of the derivative of ln of x divided by the derivative of x while x goes to infinity. The derivative of ln of x is 1 over x, and the derivative of x itself is equal to 1. So this is equal to the limit of 1 over x while x goes to infinity. 1 over infinity is 0. Even though we cannot directly use L'Hopital's rule, but since a sequence is a function, we can eventually apply the L'Hopital's rule to functions with domain as real numbers and use the conclusion here. So the limit of ln of n over n when n goes to infinity is 0. So in general, we say that if the limit exists, the sequence is convergent. Note that if the limit of a sub n while n goes to infinity exists, then we say that the sequence is convergent. Otherwise, we say that the sequence is a divergent sequence. Otherwise, we say that the sequence is divergent. Okay, give us examples. Take a look at these two examples. This sequence is -1 raised to n. Another example for you. An is -1 to the n divided by n. First of all, let us take a look at the graph of the function. How do we graph this? So we can use point plotting n and a sub n. Remember, n is a natural number, so it starts from 1, 1, 2, 3, 4, 5, 6, and the rest of it. If n is equal to 1, you get -1 raised to 1, which is -1 and negative. So let's graph it together. N and f of n. Okay. 1 and negative. 1 and negative. This is a sub 1. The second point, if you plug in 2 here into the function, you get -1 raised to 2. -1 times -1, which is +1. So when n is 2, your y value is 1. A sub 2. If you plug in 3, you get -1 raised to 3, which is -1. Very well. If n is 3, my y is again -1. A sub 3. If you plug in 4, you get -1 raised to 4, which is +1. Okay, very well. I have 4 and +1. A sub 4. We can continue this process. You can plug in the rest of the values if you have time, and you can see the L limit of the function is either 1 or -1. 1 -1. We cannot decide. This is an example of oscillating sequence. And since the limit is not a fixed number, we say that the limit doesn't exist. Limit does not exist. And we say that we have a divergent sequence. Okay, let's take a look at this function. Okay, how do we graph this? Let's plug in some points. Graph n, a sub n. So since n is a natural number, we start by plugging 1, then 2, then 3, then 4, and if you have time, you can continue this process. If n is equal to 1, we get -1 raised to 1 divided by 1, which is, okay, -1 raised to 1 is -1, -1 divided by 1 is -1. The first point on the graph of this function is 1 and -1. Very well. Let me graph this, see what's going on here. And f of 1 and -1. Then n is 1. I have -1 as the first term, a sub 1. Next, let's plug in 2. We have -1 raised to 2 divided by 2. -1 raised to 2 is 1, and on the denominator you have 2. So you get a half. Well, at 2, I have a half, a sub 2. Let's plug in 3. -1 raised to 3 divided by 3. -1 raised to 3 is just -1, and on the denominator you have 3. When n is equal to 3, my third term is minus a third. Okay, a sub 3. If I plug in 4, I have -1 raised to 4 divided by 4, which is 1/4. It seems like these terms are getting closer and closer to the n axis. So a sub 4 is a 4. If I plug in 5, I get -1/5. It's getting closer and closer to your y-axis, which is f of n. Y value is getting closer and closer to 0. So the limit of the function is 0. Limit of a sub n, while n is getting closer and closer to infinity, is equal to 0. So you have a convergent sequence. One important theorem. Very well. Theorem. This theorem says, suppose you have a convergent sequence. So let limit of a sub n while n goes to infinity is e just l. You have a convergent sequence, a sub n. Then it says, suppose you have a continuous function. Let f be a continuous function at L. Two conditions. Then the limit of f of a sub n, the limit of composition of a function and a sequence while n goes to infinity is equal to the limit of, so you can take this limit and you can move this inside the function. You get f of limit of a sub n while n goes to infinity, which is equal to f of f. These two conditions need to be met. The first one is you have a convergent sequence at which has L as its limit, and the second condition is your function f is continuous at the limits. Then you can move this limit inside, since you have composition of two functions, the limit of the composition is equal to the outer function and the limit of inside function. Okay, guys, let's apply this theorem. Example. Find the limit of sine of pi over n while n goes to infinity. We're going to apply the formula, powerful formula that we learned here. So here you have a function f. So you are finding the limit of function f at sequence a sub n while n goes to infinity. Let us check these two conditions. First condition, second condition. The first condition says the limit of pi over n while n goes to infinity must exist and it must be equal to a number. So since you have pi over n while n goes to infinity, you have a constant divided by infinity, which is equal to 0. So you have your a good here. The second condition says your function f must be continuous at L. So the second condition, since we have sine function, sine at 0, of course, sine function is a nice function, it's continuous everywhere, is equal to 0 and it is continuous. So since these two conditions are met, we can apply the theorem and we can say that, hey, the limit of sine of pi over n is equal to the limit of f of a n while n goes to infinity, which is nothing but the sine of limit of pi over n while n goes to infinity. And since we know that the limit of pi over n while n goes to infinity is equal to 0, this is equal to the sine of 0, and we know that sine of 0 is equal to 0, so this limit is equal to 0. Okay, in Math 1A, you learned about Sandwich or squeeze theorem. We're going to see the application of squeeze theorem in sequences. So, Math 1A, squeeze theorem. Squeeze theorem says if you have three functions, f of x, g of x and h of x. And suppose function g of x is sandwiched between these two functions, and for sure you know the limit of f, the limit of h, and you know that the limit of f is equal to the limit of h while x goes to a number. Suppose these two limits are just equal to f. Then this theorem says, this guy, Squeeze theorem or sandwich theorem says, the limit of g of x must be equal to f. The limit of g of x while x goes to a must be f. Okay, let's apply this theorem that we learned in Math 1A in sequences. Example. So this example says, find the limit of this sequence, n factorial divided by n raised to n, while n goes to infinity. Remember that? N factorial is defined as 1 times 2 times 3 times n minus 1 times. That's how we define n factorial. Perfect. Let us analyze this sequence. So a sub 1 is equal to 1 over 1 raised to 1. A sub 2 is equal to 2 factorial divided by 2 raised to 2. A sub 3 is 3 factorial divided by 3 raised to 3, and so on. N factorial divided by n raised to n. Okay, a sub n or n factorial divided by n to the n can be written as 1 times 2 times 3 times n over. The meaning of n to the n is the product of n by itself n times. So you have n times n times n times n. Okay, so take a look at this. 2 over n, 3 over n, n over n. So consider this expression. 2 over n, we'll just multiply this, times n, n times n times n. This expression is always between 0 and 1. If you don't believe me, just plug in different values and you can actually see it's always between 0 and 1. Note that your n goes to infinity. I'm not talking about small values of n. Your n is very big. 1 million, 2 million, 3 million, something very huge, very big. I'm not talking about 1, 2, 3. Okay, now I multiply everything by 1 over n to create n factorial divided by n to the n. Multiply all sides by 1 over n. On the left hand side, you have 0 times 1 over n. In the middle, you have 1 over n times 2 times 3 times n over n times n times n. Less than equals to 1 times 1 over n. So in the middle, you actually created n factorial divided by n to the n. On the left side, you have 0. On the right side, you have 1 over n. Okay, squeeze theorem says, if I have the limit of this function, outside function, 1 over n, and if they are equal to each other, the limit of the function in the middle must be equal to the limit of these two functions. We know that. We know that. The limit of 0 while n goes to infinity is 0, and it is equal to the limit of 1 over n while n goes to 0. So, squeeze theorem says the limit of n factorial divided by n to the n while n goes to infinity must be 0. Okay, let us define increasing, decreasing, or in general, monotone function. Definition. Let A sub n be a sequence. We say that A sub n is an increasing sequence, is an increasing function. A sub n is an increasing sequence if n is less than n plus 1, then A sub n is less than A sub n plus 1. And we say that
there's a blue line on the screen.
Okay, perfect. And we say that a sequence is decreasing. A sub n is a decreasing sequence if n is less than n plus 1, then the general term is getting smaller and smaller. If n is less than n plus 1, then the general term is getting smaller and smaller. For example, consider this sequence. 3 divided by n plus 1. First of all, let us get back to math 1a. Remember that to show that the function is increasing, decreasing, you take the derivative of the function. If the derivative is positive, you say that the function is increasing. If the derivative is negative, you say that the function is decreasing. So take a look at this function this way. Math 1a, f of x equals to 3 divided by x plus 5. Take the derivative of this function, f prime of x. The derivative of numerator is 0 times x plus 5, which is 0, minus the derivative of the denominator, which is 1, times 3. So you get negative 3 divided by x plus 5 raised to the second power. Okay, the denominator is always positive. Your numerator is always negative. So the derivative of the function is negative, and based on that, you in math 1a say that, hey, my function 3 over x plus 5 is a decreasing function. If you remember the graph of these types of function, the graph in general behaves like this. So since the derivative is negative, the function is decreasing. Okay. With the same argument, you can say that, hey, since equivalent to the sequence, the function is decreasing, this guy is decreasing. Or you can directly use the definition of decreasing sequence and show that this function, this sequence is decreasing. So let me show you. Let n be less than n plus 1. Okay. So n is less than n plus 1. This is the condition that you have in both of them. So how can I create n plus 5? Let us add 5 to all sides. I'm adding 5 to all sides. I have n plus 5, n plus 5 less than n plus 6. Why I'm adding this? An is equal to 3 over n plus 5. An plus 1 is 3 over n plus 1 plus 5. I'm comparing these two terms. So by adding 5 to both sides, I'm creating an and an plus 1. Okay, now I'm going to flip these two. Remember that. If A is less than B, then 1 over A, if you flip this, is greater than 1 over B. Like if 1, let us say 2 is less than 3, so a half is greater than a third. So when I flip these two, I get 1 divided by n plus 5, which is greater than, I have to flip the inequality, 1 over n plus 6. It's not completely the same as my a sub n. So what I'm going to do, I'm going to multiply these two by 3. So I get 3 divided by n plus 5 greater than 3 over n plus 6. An is 3 over n plus 5, so I have my an, which is greater than an plus 1. An plus 1. Which one is this? This is the definition of a decreasing sequence. Decreasing sequence. So what about this sequence? Here you have a sub n equals to n over n plus 1. There you go. So is it increasing? Is it decreasing? Equivalent to this sequence, you have function x over, I'm sorry, this has x on it. X squared plus 1. X squared plus 1. So let's take the derivative of this function, applying the quotient rule. The derivative of x is equal to 1 times x squared plus 1 minus the derivative of your denominator, which is 2x times x, divided by x squared plus 1 raised to the second power. So the derivative of your function is equal to x squared plus 1 minus 2x squared divided by x squared plus 1 to the second power. So the derivative of the function is equal to minus x squared plus 1 divided by x squared plus 1 raised to the second power. There you go. How do we decide if it's an increasing function or decreasing function? You have to look at the sign of this function. 1 and -1, and here we're looking for the sign of the derivative of the function. We're not worried about the denominator. The denominator is an expression raised to the second power, it's always positive. For your numerator is the deciding expression on the sign of the derivative of the function. If you plug in 0, you get 1, which is positive. So at 0, a random number, you get a positive sign. If you plug in, for example, 2, which is a number greater than 1, you get 1 minus 2 squared, negative. And if you plug in, for example, -2, you get the same negative sign. Very well. You can say that, hey, for x greater than 1, my function is decreasing. For x greater than 1, f is decreasing. How is that helpful? Remember that for a sub n, n starts from 1, then 2, then 3, and so on. Equivalently, you can say that the sequence is decreasing. Let me show you how to use the definition. So let n be less than n plus 1. Remember that an is n over n squared plus 1, and an plus 1 is n plus 1 divided by n plus 1 squared plus 1. So our goal is to create these terms and compare them. So what I'm going to do, I'm going to raise both of these to the second power. Raise them to the second power. So I have n squared less than n plus 1 squared. Next step, I'm going to add 1 to both sides. Add 1. Then I'm going to flip these two. I have 1 divided by 1 plus n squared, which is now greater than 1 over n plus 1 squared plus 1. Okay, perfect. So what else is missing here? What I have n and I have n plus 1. What I can do, I can multiply both of these by n, and remember that n is a positive number. It doesn't change inequality. I get n greater than n over n plus 1 squared plus 1. Very well. What else do we have? I have plus 1 as the constant. So what's the connection between this and n plus 1? What if I add and subtract 1 and use the composition of fractions? N plus 1 minus 1. Okay, here I have n over 1 plus n squared, which is greater than n plus 1, divided by n plus 1 squared plus 1 minus 1 over n squared plus n plus 1 squared plus so definition. me graph a function for you. Let me graph a sequence for you first. Consider the following sequence. Sequence A sub n has a graph like this. And f of n, and some terms of this sequence are going to be like this. So suppose it starts from here. Remember that you have a sequence. A sequence is discontinuous. That's why we mentioned that, okay, in Math 1A, we learned about f of x. F of x is a function with continuous domain, and the graph is continuous. But when it comes to a sequence, you cannot connect these dots. It's discontinuous, like discrete math. So suppose this is your A sub n. We say that this sequence is bounded above if there is a constant function like L, like M. So let's call it M. You don't want to keep confusion with L as the limit of the function. M as a constant function is the bound of this sequence. So that's the general idea of a bounded sequence. M is a bound. So let's officially define this definition. Let A sub n be a sequence. So here you have a sequence, and we say that sequence A sub n is bounded above if there is a constant. When we're talking about constant, we're talking about a constant function. It helps to visualize this better. Constant like m, such that your sequence, the terms of the sequence eventually are less than or equals to m when n is greater than equals to 1. With the general argument, we can define a sequence that is bounded below. So bounded above. Now let me graph a sequence for you that is bounded below. And suppose here you have lower bound and so we say that the sequence A sub n is bounded below if there is a constant like m such that an is greater than or equals to m or n greater than 1. All terms of the sequence are greater than or equals a constant like m.
Professor?
One theorem for you. So one sequence for you, one theorem for you about sequence. It says every bounded monotonic sequence is convergent. So note a sequence is called bounded if it has upper and lower bounds. And note a sequence is called a monotonic sequence if it is increasing or decreasing. And here we have an interesting theorem. This theorem says if A sub n is a bounded and monotonic sequence, then for sure you can say that it's convergent. Then it is